All right, everyone. Today we're going to be talking about the max power transfer theorem. And the power transfer theorem is just basically an expansion of our normal power equations, right? P equals I squared times R, P equals IV, and P equals V squared over R, okay? Now, the question that the max power transfer theorem is trying to ask is, what is the max power that we can obtain from a system like this, right? So say that we have one system right here, and then we have this other system right here, and this network system has a resistive load, RL, and the voltage difference between the two is VL, okay? So we're given that RS is some value and VS is some value. So say that this is just some, I don't know, system right here that is trying to communicate with this system right here. We're trying to find what is the max power that can be extracted from this system. And the idea is that max power can be extracted if RS is equivalent to RL, okay? So that they are matched together, all right? And the underlying formula that we are going to use to find this max power is PL equals VS squared over 4RS. Okay, and we're going to derive that right now. So the first thing that we're going to do is say let PL equal the max power. Okay, and we're going to actually use this equation right here because we have the voltage and we have the resistance, so might as well use the one that directly uses both of them. Okay, so we're going to say that PL is equal to VL over RL squared. Okay, well, the VL is squared. Now, the question is, well, this is known, this is known, this is not known, and this is not known. So how are we going to solve this? Well, we're going to have to reduce VL into something that we don't know and do know, okay? Can you think of a way to do that? Well, this right here, VL, is a voltage divider, okay? RS and RL divide down the middle to produce this VL right here. So we are just going to say that VL is equal to RL over RS plus RL times VS, because VS is the input voltage. Okay? Now we're going to plug that in. PL equals VS RL over RS plus RL, all of that squared, times 1 over RL. Okay? And simplifying this further, we're going to get VS squared RL squared over RS plus RL squared times RL. These RLs cancel out, and we are left with VS squared over RS plus RL squared times RL. Okay. Now, the question here is, well, we're not finished because we still don't know what RL is. And that is where we start maximizing. So from our calculus days, right, when we see something maximized, right, what do we think of? We think of the derivative being 0, okay? So we are going to take the derivative of this power, this max power function, with respects to RL, because that is our unknown, and we're going to equal it to 0. Okay? Taking the derivative, we're going to factor out the Vs squared to make it easier, and we are going to employ just a simple quotient division rule. Okay, derivative division rule. So I have the mnemonic ho d high minus high d ho over ho ho. So where ho is the bottom and high is the top, right? So we are going to do, and it's ho d high d ho because my old calculus professor like thought of Santa. Another one is low d high, like high d low, but that's irrelevant. Anyway, so we're going to do the lows, and we're just going to keep it the same. And the low is just RS plus RL squared. And we're going to multiply by the derivative of the top. And the derivative is, like, we have RL, and that's our variable, so that's just going to be 1 minus, and now we're going to have the high one, just a normal high one, and we are going to take the derivative of the bottom now, and that's just chain rule, 2 times RS plus RL, and all over the low squared, or ho-ho. Right, RS plus RL squared, which is to the 4th. And then close our parentheses right here. All of this equals 0. Now, immediately we can just straight up remove these guys because they're being multiplied by 0. And we are left with RL plus RS squared minus 2RL RS plus RL equals 0. Expand this out. RL squared plus 2RL RS plus RS squared minus 2RL RS minus 2RL RL squared equals 0. Okay? Now here's the neat thing. We can cancel this out and cancel this out, and we get right here RL and RL, they subtract together, so we get RS squared minus RL squared equals 0, and we simply get RS is equal to RL. So this is when power is maximized. As we proved this, right? I said before that the load should match the system that we know, okay? The system that we can't change. So there we go, proven. And we can now see that this is true, okay? Because we can just go back to our formula. PL is equal to, I don't know why I have a bracket here, is equal to this guy right here, RL Vs squared over RS plus RL squared. And we can just simply plug in RS. So RS Vs squared over, and then this is just 2RS now, squared, which is equal to P equals, in drum roll, Vs squared over 4RS. And we just proved it. We proved that the max power, PL, is equal to Vs squared over 4RS. Awesome. Now let's go do some practice problems. So the first practice problem, super easy. We're straight up given RS equals 8 ohms and a voltage source of 4 volts. And we want to find the RL by which max power can be extracted. Well, from what we had derived previously, for a system with just a constant current, a constant voltage source, and an R equivalent, RS equals RL. Okay, so that means RL is equal to 8 ohms. Okay, And we are also asked to find that power. So using the equation that we just derived, PL equals Vs squared, which is 4 squared, over 4 times 8 equals 16 over 32, or 0.5 watts. And so this is the maximum amount of power that can be extracted from this circuit if RL and RS are set to be equal. Okay. Now this was a super simple one. Highly recommend you memorize that PL equals Vs squared over 4RS, but you need to make sure that this system can be simplified down to one Thevenin and one R equivalent. Okay? Okay, now this is a more realistic problem. The other one was basically, spoon-fed to you. So in this case, we want to find the Thevenin and the R equivalent so that we can put it into this circuit form, so that we can find the PL, the max power. Okay. So the first thing we're going to do is disconnect the network. Okay, so we're just going to delete this. Okay. And we're going to have A and B. And so this is effectively now VAB. Okay. And I am just going to call it VS for simplicity's sake. So that means, let's see what kind of nodes that we have. We have one node right here, and we have one node right here, and we have one node right here. However, this is a voltage source, so we're also going to have to count the node right here because it's being forced. 10 more volts are being forced into from this node to this node. So this is effectively called a supernode. And I should have gone over this in Unit 1. I went over super loops, but I am expecting to make a bunch of other practice videos, and you will be able to get more practice with this right here. And the reason why we're going to do this is because it eliminates a variable. Rather than saying this is Vs, which it is, so Ns, and then this is V1, let's just say, and that's N1, and this is V2, right? Actually, let me just call this V2, and I'll just call this V3, so that we have the same number convention. This is V3. Instead of calling this V4 and introducing a fourth variable, let's just say that this is V3 plus 10, okay? And let's turn this lowercase n into a big N to show that it's encompassing all of this, okay? So step 1, remove network completed. Now step 2 is apply this nodal analysis to find that Vs, okay? Because eventually we're going to want to turn it into our simple network, right? Boom, oops. Boom, boom, boom. We need this Vs and we need this Rs, okay? So let's go ahead and apply the nodal analysis. Hopefully by now you know the drill, right? We're going to do N1. And N1 is simply going to be V1 minus 4 over 6 plus V1 minus V2 over 3 plus V1 minus V3 over 2 equals 0. And then we're going to go ahead and simplify it out. And for that nodal equation, we get 6V1 minus 2V2 minus 3V3 equals 4. Now we're going to simplify N2. N2 is right here in the middle. And we're going to say we have V2 minus V1 over 3 plus, and now this time we have V2 minus this whole thing, V3 plus 10. V2 minus V3 plus 10. And 8 ohms. And we have a current source driving it this way, so outward, so plus 3 equals 0. Once again, we're going to simplify this. I'm going to multiply by 24. And we are left with negative 8V1 plus 11V2 minus 3V3 equals negative 42. And finally, we are going to solve the supernode. So the supernode, think of this as the whole node. Okay, that's why it's called a supernode. So then that means we're going to have to take into account the current this way and this way. Okay, not just this one. Okay, we have to include this also. So we are going to have V3 minus V1, and I believe it's 2 ohms. Yes, 2 plus V3 plus 10 minus V2 over 8 equals 0. We're going to multiply it out by 8. Okay, and we get negative 4 V1 minus V2 plus 5 V3 equals negative 10. I'm going to go ahead and put this in a matrix. And we're going to go ahead and solve this out, and I'm going to get V1 equals negative 14 volts, V2 is equal to negative 18.6154 volts, and V3 is equal to negative 16.9231 volts. Okay, and we can see here that Vs is just V2 because it's the voltage difference from ground to V2, so it's just going to be that magnitude. So our answer for Thevenin is negative 18.6154 volts. Okay. Now step 3 is to find the R equivalent. Okay. So what we're going to do is we're going to copy down this entire circuit, but we are going to remove all of the sources. Okay, so we're going to remove this, we're going to remove this, we're going to remove this, and we are going to replace all current sources with an open circuit. So we have a current source right here, and we're going to replace all voltage sources with a closed circuit, like so. And now we can solve for R equivalent. We can immediately see that 8 and 2, they're in series. So we'll just do 8 plus 2 equals 10 up here. And we can see that 10 is just hanging there because this is stopped. The open circuit, no current flowing through there, completely ignored. And we can also see that these guys are now in parallel. Okay, so we're going to have 10 in parallel with 3 is equal to 10 times 3 over 10 plus 3, which is equal to 2.307. And that whole configuration is in series with 6. So we are going to have 2.307 plus 6 equals 8.307 ohms. Okay, and so our R equivalent is equal to 8.307 ohms. Nice. Now let's not forget what let's not forget what we're actually solving for. We're looking for the max power. And now we have effectively reduced this circuit to have a Vs and an Rs, or R equivalent. So let's go ahead and put that into a circuit. So all that very complicated circuit reduces down to simply a voltage source and an RS, or R equivalent. And that R equivalent is 8.307 ohms. And that VS is, what was the VS? Negative 18. Negative 18.614. Okay? And RL is our network. That's the network that was inside of it, inside of this guy right here. This guy. Okay? Cool. Now we are going to apply the max power transfer theorem. Remember, RL is equal to RS, so therefore RL is equal to 8.307. So this guy, the network, ideally, if we want max power, should be 8.307 ohms. Okay? And our PL, the max power we can extract from this, is going to be negative 18.614 squared divided by 4 times 8.307. And the max power is, let me grab my calculator, 10.4289 watts. And that's the answer. And this is how you find the max power of a circuit that has a network attached to it.